Numbers are great for quantifying all sorts of things, like how much mass an object has, or the amount of flour you need to buy from the grocery store. But they can't always quantify something like force or something like speed, or sorry, velocity, because, well, the thing with force, I can say, yeah, I'm applying 1,000 newtons of force, but in which direction, right? If I'm applying 1,000 newtons of force on this like lawnmower, to completely quantify that force, you need to give it a direction. That's where vectors come in. Vectors are used to quantify these things that have both a magnitude, right, which a number can describe, but also have a direction. So the way we kind of represent vectors is with an arrow, right? Pretty simple. I'm sure you've seen it. Boom, vector right here. And if I want to label this vector, I give it some letter V, and then I add a little arrow on top, or on a test or in a book, they'll bold it. So that's just the notation there. But what makes vectors useful is that we can kind of, like I said, we can kind of quantify a lot of things with them. And let me just grab a note sheet here so I remember where just so I can hit the key points, right? So with vectors, right, you can quantify things like force or speed, right, by kind of saying that, hey, like on a free body diagram, when you draw your force, this arrow that you're drawing for like the weight, or for like, well, I guess you wouldn't draw weight like this, but for whatever force, that is a vector. You're drawing a vector to quantify that, at least like, or to kind of, what's the word? I guess represent the force. There we go. So if I draw another vector, u, right? These vectors are actually equivalent. They're equal if they have the same length, right? If their lengths are the same, which we call magnitude, and if their directions are the same. So in this case, their directions would be the same if you think about kind of the angle from the horizontal, right? So if you think about the angle from the horizontal, if those angles are the same, then boom, they're going to be equivalent. So you can, with vectors, you're not dealing with numbers anymore. You're dealing with a new kind of quantity, and there's going to be some rules like on how we can operate, like how we operate on these vectors. We have to define. So to define vector addition, we'll talk a little bit more about the algebra in a second, but just to kind of get an idea of what vector addition looks like, if I were to do v plus u, I would take v, and I'm just gonna say, just for the purposes, this isn't the same vector, it's a little bit shorter, but I would take v, and then I would then take the tip of u, and I'll actually also direct u more like this. There we go. I'll take the tip of u and then draw it to, I take the tip of u, draw it from the tail, or sorry, I would take the tail of u, that's the end, and I would add it to the, I would kind of add it to the tip of v, and I would draw the resultant vector as kind of from the tip of v to the, or the tail of v to the tip of u. There, oh my god, that was a handful, or a mouthful. But this is by definition how we kind of add vectors, right? So we can, vector addition, that's one thing we can do, but we can also work with scalars. So, if a vector has magnitude and direction, a scalar is just the magnitude, right? It's a number. A scalar is really just a number. It's a magnitude. So, or it represents magnitude. So if I take v, and I'm showing you all the geometric representations first, because I do want you to get like kind of an understanding of like what this really looks like. If I take v, or if I say v is going to equal to 2 times u, right? If this is u, then v is going to be twice the magnitude. So 2 times u is going to equal v, right? I could say w is equal to 1/2 of u, so then it would be 1/2 the magnitude. Notice they're still directed the same direction, right? The direction will not change from a scalar multiplication unless, let me just try to finish this out, unless you add a negative sign. The negative sign will make it so that the vector is now going the opposite direction. So if I say negative u, right, that would look like sure, negative 2u. Say magnitude is 2u, but now we're going negative, we're going the other way. So that helps us define vector subtraction. Vector subtraction is, and also one quick note, I want to note, this is a cumulative thing, right? What you're going to notice is a lot of the algebra rules that we've known before, they don't transfer over to vectors, right? Did I say cumulative? I meant it's either commutative or it's one of the rules where v plus u equals u plus v. That actually holds, right? Because if you go u first and then v, you would actually get the same resultant vector, right? Because if you go u and then v, you're actually creating a parallelogram, and the diagonal would be the same for both. So you're going to notice not all the vector rules, like not all of the algebra rules work over to the vector algebra rules that we're used to, but a lot of them do, and we can prove it like geometrically and soon algebraically. With vector subtraction, what you're really doing is you're really saying, well, if I want to do v minus u, this is the same exact thing as v plus negative u. Well, hey, I know how to add vectors, so I can just say v, and then u, negative u, would look like this, right? It would be the flipped over version of u, so I would just add in then minus u, and then boom, I get v minus u, right? So, another way you can kind of think about it is, well, if you have v minus u, how do you go from, or I guess not another way to, yeah, I guess another way to think about it. Like if you had v minus u, how would you go back to v? You would need to add in a u, right? You would use your tip to tail like that to get back to v. So that kind of shows you that you have to kind of flip u the other way around to go backwards essentially, and that would be the same as doing v plus negative u. That's where v minus u, or that's how vector subtraction kind of works. So we're doing a great deal with the geometrical representations. Well, mathematically, what do vectors actually look like in terms of numbers, right? A lot of representations, but what do they mean in terms of numbers? Well, you can define a vector using a coordinate system, right? That's where it's the most useful, right? Really, who cares about vectors in free space? We need a coordinate system to kind of ground things, kind of figure out where things are. So for our traditional y-x plane, right, a vector, you could draw it like that, you could draw it like that, you could draw it coming from the origin, and the main deal is that, well, a vector will have a component in the x direction and a component in the y direction, right? I'll say, so if this is v, I'll call this vy, I'll call this vx. And so you will have these components, and I can define this vector v using this notation. So I can say, I use this bracket vx, comma, vy. And vx and vy, these are numbers. They're not vectors, they're numbers. And, right, so depending if I had, something like 4, 2, right, that would look like 4 this way, and then 2 up, so it would look like that, right? So 4 and then 2. How do I find the magnitude? Well, that would be as simple as Pythagorean theorem, right? Or using the distance formula, if you know your point. Or actually, no. Well, we'll forget that. It's just Pythagorean theorem. 4 squared plus 2 squared is 16 plus 4, 20. And so the magnitude would be root 20, which is also equal to 2 root 5. So the magnitude of v, I use absolute values for that, is going to equal 2 root 5. We can do the same thing in 3D space, or I guess that is just space. space is, I guess, inherently 3D. So if I were to draw a vector, like, I'll do it coming from the origin just because it's going to be the easiest to kind of show. But this vector might point to some point P, and the components of this vector, it's going to have some components in the x direction, it's going to have some components in the y direction. I need to draw that better. It's going to have some component in the y direction, and then it's going to have some component in the z direction. So this vector, I'll call u, is defined as v or ux, uy, and uz. We're just adding that third dimension to the vector. That's all we're really doing. So that is how you can think about components, and you can also use Pythagorean theorem, right, to find this length, because magnitude is really just a length when you're looking at it like visually and geometrically. We're gonna say that you can use Pythagorean theorem, because if this is this is ux, this is uy, this is root ux squared plus uy squared. So really, you get that the magnitude of u is going to equal square root ux squared plus uy squared plus uz squared, because then you get this root thing squared plus uz squared equals magnitude u squared, and then you just take the square root. So it all derives from Pythag, which is pretty nice. But yeah, that's vector. That's really the essence of components, right? And another thing is, you might not always know really the components, but you might know the magnitude and an angle, right? Maybe you know that the angle from the vertical is, let's just say 30 degrees, right? In that case, if I know the magnitude is 2 root 5, I can figure out this angle, right? Because I can just say, or I can figure out the components, because I know from kind of trigonometry that Vy, or Vx, sorry. I flipped. That's embarrassing. This should be Vy, this should be Vx. I'm really sorry. Hopefully you've noticed that and you knew I was wrong. But I know Vx is just going to be the magnitude sine 30, right? In this case, sine 30 degrees is sine 30 degrees is 1/2. So, wow, wait, that's actually, oh, wait. Okay, yeah. Okay, I was like, wait, 2 root, because I was going to do 2 root 5 times 1/2, and I was like, wait, that isn't equal to 4. Well, it's impossible. You can't, this wouldn't be equal to 30 degrees. It might be a little bit less, might be a little bit more, but it wouldn't be equal to root 30. But so I guess we should really, let's just call this u. Let's just change it up and call this u. Or no, let's just call it w. If you knew the magnitude of w is root 5, 2 root 5, then I know that, and I know the angle is 30 degrees. I know root wx is going to equal root 5, and then wy would be 2 root 5 cosine 30 degrees, which is 3 over root 2. So times root 3 over 2. Oh, yeah, root 3 over 2, which is going to equal root 15. So I know w is then defined as root 5 and root 15. Yeah, and I can also find the angle. So for example, back to vector v, right? How did I know that 30 degrees couldn't really necessarily produce 2 and 4? Well, I can use inverse trig to kind of figure that out, right? Because I can say tan inverse of 2 over 4, right? Opposite over adjacent will equal theta. Because I know tan theta would end up equaling 2 over 4 or 1/2, and I can use a calculator to kind of figure that out. So that's components for you. And the deal is that, well, I can actually right, if what I can do now is I can add vectors mathematically, or I guess with numbers, right? Like u plus v, so I guess I can start erasing things. Now that we have components, we can kind of say that, hey, u plus v, so u plus v is really the same thing as u. I'll use, do they use numbers? Yeah, I think they do. Yeah, I'll use numbers. So it's going to equal u1 plus u2 plus u3 plus v1, v2, v3. Remember, I'm not adding vector notation here because it's not a vector, right? I'm not making a vector of vectors. I don't think, no, that can't be a thing. I don't think so. But also I'm not that advanced in math, so maybe I don't know. But these are numbers, right? They're representing the magnitude of the component. So if I were to add these, this is actually the same as doing u1 plus v1, u2 plus v2, plus, comma, u3 plus v3. And you can actually prove this with algebra. You can actually prove this. I'm not going to, but you can if this, you know, you want to, or by prove this, I mean you can prove that this actually is the same thing as doing tip to tail. With geometry, you can prove. I'm messing up my words, but u minus v, you can imagine it's going to be u1 minus v1, comma u2 minus so on and so forth. You know, because this is really the same thing. This is really the same thing as the u vector plus negative, and then all your components. And then if you have a negative, that actually you distribute the negative over to each component. That's another thing, right? If 1/2 of v1, v2, v3 will equal it'll equal 1/2, or it'll equal a vector with 1/2 the components, right? So that's another thing, right? That's how scalars will work. And once again, you could prove this is the same thing as just having the same vector with like the length doubled or whatever, or the length halved. You could actually prove that that vector would have these components with some, I guess, geometry. So there's a bunch of properties, right? I can show you the properties. I'm not going to list out each of them because you can honestly kind of Google them. But there are a bunch of properties that I guess I'll show you right here with my iPad. Yeah, there's a bunch of these different properties that you could prove pretty simply, I guess. I guess not like, they're pretty, I guess, intuitive in a way. But they're intuitive, but that doesn't always mean that all of the algebra rules apply. We're going to see with dot product and cross products, it's not always the case that the things in the scalar world transfer over so quickly or so easily. But you can prove those for sure. Like stuff like the commutative property, or that, you know, a plus 0 equals a, because, you know, the zero vector is just a vector with components all 0. So if you do your addition rules, you just end up with the same vector. Simple things that seem like they should just work whatever, you can make sure they work because vectors are different from scalars. Another quick thing I want to just touch on is the idea of your standard basis vectors. So I erased the coordinate system. I guess I'll just draw it again. But with your coordinate system, just keep in mind that, or not keep in mind, another way you can represent vectors is, you know, you have these standard vectors that are unit vectors, which means they have a magnitude of 1. And we call them I hat, j hat, and k hat for each direction, where I hat is defined to be 1, 0, 0. J hat is defined to be 0, 1, 0, and then k hat is defined to be 0, 0, 1. So these just give you these are called unit vectors because they have a magnitude of 1, and you can actually write vectors as a sum of these vectors, vectors, right? For example, the vector 2, 3, -2, that's the same thing as 2i hat plus 3j hat minus 2k hat. And this is because, right, you could say this vector is the same as 2 times 100, which is really just 200, plus 030 minus 00, -2. And when you add those vectors, you just get back this vector. So this is just another kind of notation you might see with vectors. And if you want to find the unit vector with any direction, right? These are just directions along your axes, but you can actually find the unit vector. So for a vector like this, right? You can find the unit vector that has the same direction. So for something like 2, 3, -2, which would not look like this, but to find this unit vector that once again has magnitude 1, what you gotta do is, well, you kind of gotta think, right? I guess here I can show you like this. You have to divide each of these components by some number a, right? You have to reduce these components so that when you take the magnitude, it will end up equaling 1. So if you do 2 divided by a squared plus 3 divided by a squared plus -2 over a squared needs to equal 1. Well, I get 4 over a squared plus 3 over a squared plus 4 over a squared will equal 1. And I can just, square both sides. And I still have 1 on the other side. So now, common denominator, so 4 plus 3 plus 4, that would end up equaling 16, I think, right? Maybe? No, I messed this up because this is a 9. Okay, 4 plus 4 is 8, 8 plus 9 is 17, so I get 17 over a squared is equal to 1, or I get a squared is going to equal 1 over 17. No. Wait, yes? Yeah, I do get 17. Wait, a squared equals 17, or a is going to equal plus or minus root 17. So, I can actually multiply this by 1, or plus or minus, right, root 17, and I get a unit vector. So the components would be 2 over root 17, 3 over root 17, -2 over root 17. And yeah, like that's that would give you a unit vector with the same direction as 2, 3, -2. So the general formula is what we really did is the magnitude of this vector is root 17, so we're dividing it by plus or minus. So the unit vector v hat, the hat, by the way, means it's a unit vector, is going to equal just v over the magnitude of v, which is what we did right here. The magnitude is root 17. We're really just dividing it, I guess, plus or minus. But I think v hat by convention might be a principal root thing. But you could also have a unit vector. Oh, wait, yeah, it's going to be just plus. We're using just plus. I forgot. But if you had the minus solution, that would be a vector that's parallel, just in the opposite direction. So yeah, this is a quick overview of the basics of vectors. Yeah, I mean, I could do some examples, but I figured why waste your time more? This has been the basics of vectors, and we will talk more about them extensively throughout our MV calculus journey, but specifically we'll talk about dot products and cross products in future lessons.